Good morning and welcome to the Calculus of Functions of a Complex Variable. I want to take this presentation to get us started before we actually start covering material, and I want us to look at why we're actually wanting to study functions of a complex variable, what we're going to do, some of the topics we're going to cover, and also a little bit about how we're going to approach the whole thing, because this course can, for some of you, be the first post-calculus course, and the ballgame is changing a little bit, and we want to be prepared for that. Alright, so why would we want to study functions of a complex variable? Well, one of the big reasons is that complex analysis has lots of applications. Now, for us, that will mainly mean the theory of harmonic functions, and here's where I'm sometimes a little bit less than enthused about the applications, because the harmonic functions, which are important in heat transfer, for example, and also in wave phenomena, well, the harmonic functions in complex analysis are two-dimensional, whereas, of course, our world is three-dimensional. So these applications would be limited to cases of that have a certain kind of symmetry in the third dimension. However, there are many other applications which unfortunately go a lot deeper than our course will go, and among those applications are spectral theory, Fourier analysis, and number theory, and here's where you really cover three large parts of mathematics. Spectral theory goes into the really abstract realms of still applied mathematics. Fourier analysis is highly applied, and number theory is considered a very pure branch of mathematics. However, with recent events in public key encryption, well, recent as of 20 years ago or 30 years ago, public key encryption actually makes number theory also applicable. However, these three branches are just very widely spread across the mathematical spectrum. From an educational point of view, we will get first exposure to the idea of a proof, or further exposure if you already have taken a proof classes, or if proofs were emphasized a bit in your calculus classes. We will get a lot of practice in working with complex numbers, including becoming really secure in computations. That is something that I've even noticed in myself as I prepared this course. I mean, of course, I could work with complex numbers before this, just like you can, but certain computations that previously I had to think about are a lot more automatic now. And in fact, when I once talked to an electrical engineer who said that complex analysis would be a good course for electrical engineers to take, I was asking why, and I was expecting an answer along the lines of, well, there are all these wonderful applications, but this gentleman actually said, well, after you're done with this class, working with complex numbers is just not a problem anymore. It's this very practice in working with numbers, because a lot of electrical engineering ultimately can be boiled down to complex algebra. All the stuff that electrical engineers doing with Laplace transforms requires a lot of complex, really complex algebra, not even complex analysis. We will also get a lot of practice in two-dimensional visualization. Of course, the complex plane is two-dimensional, and we'll be drawing a lot of curves in there, so that is very helpful in visual thinking. And the key word there is contour integrals, which will take up a good part of the course, that we're going to integrate over contours in the complex plane. And finally, and this is really a mathematical reason, complex analysis is extremely pretty. Differentiable functions of a complex variable, and well, whenever you do anything that is related to calculus, differentiability is pretty much the standard property that you demand of those functions. Differentiable functions have a lot of nice properties that differentiable functions of a real variable simply don't have. Okay, so what are we going to do? Well, we're going to start by formally introducing complex numbers, and that's a little bit different from what we're used to from, say, calculus, for example, where we basically say, well, you know the numbers, now let's work with them. We actually will go from the point of view that in mathematics we can only use what can be proved, and so we will start saying, well, the real numbers work like they always did, but how do we construct the complex numbers actually? Along those lines, I have to say right away that learning how to do proofs takes time. Some of the homework problems and some of the presentations as we're doing proofs will be a bit demanding, but it is a first step towards building proofwriting capabilities, and it is well worth doing. Similar to learning how to do proofs taking time, it also takes some time getting used to the axiomatic method, which says, well, there are certain axioms, certain hypotheses from which we start, and everything else we have to derive from that. But again, this is essentially how mathematics, pure and applied, technically does work. We have a certain set of axioms, which is actually a fairly small set of axioms, and once we have established those axioms, everything else is derived from them. The course also gives valuable first or additional practice in calculus, in these kinds of methods, while at the same time we will also keep some of the elements of a calculus type approach around. So that goes along the lines of something that Michael Spivak, a very well-known differential geometer, once said, and that is, computation is good for the soul. Some of the computations that you'll see here will be extremely involved, actually, or more involved than what you may have seen in calculus. Let's not get scared here. It's not extremely involved, but maybe a bit more involved than what you've seen in calculus. But after you've done proofs, you'll realize those computations actually feel rather nice because you just compute, and that's rather neat. Overall, the whole thing then is basically a combination of visual things about complex numbers that you've seen already, like, for example, that complex numbers are re to the I theta, and then if you have two complex numbers like that and you want to multiply them, well, you add the angles and you multiply the magnitudes to get the product of these two numbers. So we will talk about a lot of stuff in complex analysis at this visual level, but at the same time there will also be an abstract layer that will actually take the definition of what it means to take a number of the form re to the I theta, or two numbers of that form, and we will take those definitions and work out from those definitions that the product really is obtained by multiplying the magnitudes, the radii, and adding the arguments, adding the angles theta 1 and theta 2. Big warning there. For many, if not most, exercises in this course, there will be no examples to mimic, and that is because the only example that can help with a proof is the proof itself, and similarly with the computations, often the only example that can help with certain computations is the computation itself. So if you have consciously or unconsciously in your calculus classes mimicked examples, and notice I'm not saying that that's bad. For me, jumping from calculus to classes like this also was quite a jump, and I never consciously mimicked examples, but there's something in the approach that people take towards calculus that needs to be refined as we go to these advanced classes, and that can be a bit discouraging. We'll talk about that also in the section on how we can do these kinds of things. So, well, right now, don't get discouraged. You can get through that, believe me. I have, and a lot of other people have too. Okay, other things we'll do, we will formally introduce differentiable functions. So that means we will get more practice with formal limits, but at the same time we will very quickly move on to derivatives, and that reflects the historical fact that derivatives and integrals take center stage in calculus, and if I want to be completely honest, derivatives and integrals also take center stage in most of mathematics and most of analysis at the abstract level. It's just that we need limits to provide the ability to formally justify everything. We will also analyze the geometric nature of many of the functions that we consider, and that is a bit different from what we've done on the real line, because on the real line, well, you just map intervals to intervals and you have graphs, but that's not the geometric nature I'm talking about. The nature I'm talking about here is a great way to practice visualizations. Take a look, for example, what the function f of z equals z squared does to certain curves. If you start with a hyperbola, let me pull that back here real quick. If you start with a hyperbola, stay there. If you start with that hyperbola and you square it, well, basically that picture is transformed into another picture, obviously. But you can visualize the transformation almost continuously. And what you end up with at the end of the transformation, the square of that hyperbola in the complex plane, I need to move a little bit further, actually is a straight line. So the way in which we're going to practice visualization here is that we're actually going to think about how curves in the complex plane are input into these complex functions and what the output curve looks like, and we will do similar things then also with regions. And that is certainly something that then has this dynamic aspect to it that you can see in this animation here, and when we get to the respective situation we'll actually see the animation a little bit larger also. Okay, what else? We will integrate complex functions along contours in the plane, and that's really a very big topic. That is something that applied people definitely remember from complex analysis. And well, on one hand, on the theoretical side, because of the way these contour integrals behave, complex differentiable functions, so differentiable functions of a complex variable, are locally equal to their Taylor series, which is something that cannot be said for real differentiable functions. And a wide variety of problems, including a variety of improper real integrals, and that's really where the exclamation mark in this statement is, including a lot of real integrals, can be solved with integrals in the complex plane, and these problems cannot be solved any other way, which is very interesting. So these contour integrals ultimately will be integrals over contours like squares, for examples, and the neat thing is they can be solved by just computing certain values at certain special points inside the contour, and that's the residue theorem. We'll talk about that in greater detail. And then improper real integrals can be computed via growing contour integrals. Of course, an improper integral across the whole real line, for example, that's something where your contour would have to have one infinite boundary, and then, well, how do you close that up into a closed contour, which is what we will talk about a lot in complex analysis. And the trick is, well, an improper real integral is something that you get by growing your real interval out to infinity, and of course any interval can be closed up to a closed contour with a semicircle, for example, and then we simply have to grow that semicircle larger and larger and then trick around with what happens on that semicircle, and we'll have quite a bit of fun with that. We will also do things such as filling in some things that we have known for a long time, such as prove the fundamental theorem of algebra, which says that every non-constant complex polynomial has at least one complex zero. And well, we have learned that a long time ago, but now we'll also be able to tell why it is true, and that is satisfying from an abstract point of view. So this is the kind of thing that again leads us more into the abstract mathematics, into the proof-based mathematics. How are we going to do that? Well, there are some tips for listening to these kinds of presentations and for watching them. And the biggest thing is we will need to digest a lot of information. But we are limited here, right? We are limited to one panel. And so unlike if I were in a face-to-face presentation where I've got 4, 5, 6 boards and can point to the beginning of the presentation, to something that we may have derived 10 minutes ago, which is now 6 panels ago, I cannot point back to that without scrolling through everything. Sometimes I might actually do that, but you can also do that. And one way to help this limitation of this screen is to open the slides for the presentation or slides for previous presentations in another window. And so if you, for example, in the next presentation have to remind yourself, well, what does it mean to be associative? Well, open up the slides, look back to make sure you remember the definition or remember what commutativity is, and so on and so on. Another thing then, of course, rather than the quick switching, is that you, of course, would stop the presentation. That is also why, if you've seen other presentations that I've recorded before, I'm not hesitant at all to go rather quickly through those presentations, because you know how to rewind, you know how to stop, and that is something that I hope you don't have to do too quickly, because that would then mean that you're absorbing information at a very quick rate. But at the same time, if you have to do that, if you have to stop a presentation and rewind it 5 times in a certain place, don't be shy to do that. I've had students in my office and office hours who said, yeah, at that point, we rewound this thing 5 times, and then when I heard we, I thought, well, there's 5 guys sitting there with popcorn watching me on a big screen or so. Hey, if that works, and if you can get the mathematics out of it, go ahead and do it, but remember, rewind as necessary, and if worst comes to worst, send me an email. We can communicate through things like DimDim, and you can also just stop by in office hours if you're local. Okay, so when there is a backward reference, really stop the presentation, go to the appropriate point in the slides to double check the claim. That is analogous to mathematical reading. As you read the text for this class, you will also find yourself frequently flip back to double check things in the book, and that is entirely normal as you're reading advanced mathematics. Go ahead and do it as necessary. Putting slides and videos side by side can help with these kinds of cross-checks, especially widescreen computers are becoming more and more popular. I like those myself. And then you could, for example, put the video and the slides side by side and really double-check whether the theorem that I am referencing really applies to what you're doing in the presentation. And finally, hey, when times get tough, and it's likely they will, the transition to proofs and to more abstract stuff is something where almost anybody I know ultimately runs into a wall. The only gentleman that I know for whom that may not have happened started taking college classes at 12, 1, 2. That was the age. He stopped or graduated from high school at age 16, I think, stopped attending high school classes, probably around 14 or so, and just was taking classes through dual enrollment credit and the like. He graduated college at 18 and obtained a PhD from Princeton at age 23. So if this young man never hit the wall that I'm talking about, he's not really the standard type of person. He was very talented, still is very talented, and in some ways the ones who knew him actually were wondering why it took him 5 years to get a PhD instead of 4 years. He was that bright, and still is. On the other hand, if you absorb this stuff very quickly, if you take to it like a fish to water, hey, maybe you enjoy this stuff and want to become a mathematician and want to take more abstract classes, that's also something that is nice. I certainly enjoy my career, and if you're interested in that and are likely to enjoy it, I can highly recommend it. But when times get tough, and when they will, remember you didn't get to this point by taking it easy. Even if calculus and other things may feel easy at that point in time, believe me, you worked there too, you needed a good brain to get through that too, and you still have that brain. So you ought to be able to make it through somehow, and the difficulties that you may have come from some changes in the approach, such as proofs, and that, like I said, is something that takes most people some time to adjust to, and other difficulties may come from the fact that computations are becoming more complicated and are paired with visualizations. And here's where I have to say that you have made that type of jump before. For example, when you went from single variable calculus to multivariable calculus. So the upshot of this quick pep talk last slide is, it is possible. Don't get discouraged with the whole thing. If things get really, really weird, hey, stop by my office, email me, we can try and talk things through DimDim if you're not local and want to do a face-to-face conversation. But this is the kind of thing that I'm here for, aside from just answering questions about the material. Every so often, I just have to tell people, look, yes, it is bad, it feels bad at this point in time, but it is not as bad as it seems. It is something that we can get through. And with that, let's actually get started with some mathematics. I'll see you in the next presentation.